Our first example of solving the radial equation will be the infinite spherical well. So in that case, the spherical well, V of r is equal to 0 inside the well, r less than a, but it's infinity outside the well. So I've rewritten the radial equation in such a way so that I'm defining k as the square root of 2me over h bar. The assumption again is that psi is going to be 0 outside the well. This is the solution inside the well. And of course my boundary condition is that u at a will be 0. This could be rather messy. Let's do a simple version of this first, and then make it a little bit more complicated. Suppose L is 0. That should make that first term will go away. And that means I've got the second derivative of u with respect to r is going to be equal to minus k squared times u. And the solution to that, of course, is just u of r is equal to a sine kr plus b cosine kr. But as r approaches 0, u of r will blow up unless we restrict b to being 0. That will get rid of that second term. The function won't blow up. So we can say then sine of ka is equal to 0. That tells me ka is going to be some integer multiple of pi. Or if I want to take it further, k then is just n pi over a. That tells me for my energy eigenvalues in that case would be e sub n 0 for L0, n squared pi squared h bar squared over 2 ma squared, just as I had before. And of course n goes from 1, 2, all the way up, as long as it's an integer. So it looks like a one-dimensional infinite square well. If we normalize that function, of course we'll get that a is going to be equal to the square root of 2 over little a, as we did before. And since L is 0, y0, 0 of theta phi is just 1 over the square root of 4 pi. Therefore, I can write psi of n0, 0 as just sine n pi r over a divided by r. Divided by the normalization. 1 over square root 2 pi a. So the stationary state psi is a function of 3 quantum numbers, n, l, and m, but the energy itself only depends upon n. Now, suppose L isn't 0. That was a really simple case, but suppose L isn't 0. I'm looking for the general solution of this radial equation, and it turns out that I can write it as u of r is equal to a times r j sub l of kr plus b times r n sub l of kr. Again, this is a well-known differential equation. J sub L is defined as the spherical Bessel function. N sub L is defined as the spherical Neumann function. Of order L. Each of them are of order L. And I can write them J sub L of x is equal to minus x to the L, 1 over x d dx to the Lth power sine x over x. N sub L of x is equal to minus x to the L, 1 over x d dx to the L cosine x over x. And if I look at a few of these, J naught of x is equal to 1. N naught of x is equal to 1 over x. J1 of x is equal to x over 3. N1 of x is equal to minus 1 over x squared. Now, at the origin, Bessel functions are finite, but Neumann functions blow up. So for our radial solution, B must be set equal to 0 because this would blow up otherwise. And so my radial solution looks like R of R is equal to A J sub L of K R. Now R of A is 0, so we have to choose K such that J sub L of Ka must be 0. That means the Bessel function has to have a 0 at K times A. Well, the problem is that Bessel functions are oscillatory, but the zeros have to be computed numerically. Well, suppose we call beta sub NL, let's define as the nth zero of the Lth Bessel function. Then K would be equal to beta sub NL over A. And therefore E sub NL would be equal to h bar squared over 2ma squared beta sub NL squared. That means our eigenfunctions will become psi of n Lm, put all of it together, A sub NL, J sub L of B, of beta NL over RA, beta NLR over A, Y sub LM of beta and phi. And we determine A sub NL by normalization. Each energy has two L plus 1 values of M. So we say that each energy level is 2L plus 1 degenerate. That brings us to probably the most famous three-dimensional Schrodinger equation to solve. That is the one for the hydrogen atom. Let's begin with this today. We may have to continue into the next video. So let's do that. Hydrogen atom is kind of like the gold standard. If you think you come up with a new idea in how physics works, you better make sure it can solve the hydrogen atom, or you're stuck at square one. So we're going to take one proton, put it at the center of mass, put it at the origin, and of course the potential is just the Coulomb potential. I'll write it as minus e squared over 4 pi epsilon naught times r. Good old Coulomb potential. We have bound states for the hydrogen atom, and we can also use it for scattering states if we had 2 negative charges or 2 positive charges. Of course, in this case, we have an electron and a proton who are going to attract. So we have bound states. I'm going to write the radial equation, minus h bar squared over 2m, second derivative of u with respect to r, plus, put my potential in, minus e squared over 4 pi epsilon naught r, plus h bar squared divided by 2m, l plus 1 divided by r squared, times u is equal to e times u. So that's my radial equation. My radial wave function then, for that I'm going to use kappa, define it as the square root of minus 2me divided by h bar. Kappa is going to be real since e is less than 0. It's an attractive potential. Rewrite this, I get 1 over kappa. Second derivative of u with respect to r is equal to 1 minus me squared divided by 2 pi epsilon naught h bar squared kappa times 1 over kappa times r plus l times l plus 1 divided by kappa r quantity squared all times u. Okay, so that's what my radial equation becomes. Let's let rho be defined as kappa times r, and let's let rho naught be defined as me squared divided by 2 pi epsilon naught h bar squared times kappa. Let's make the variables look a little better. Our equation now looks like d, second derivative of u with respect to rho is equal to 1 minus rho naught over rho plus l plus 1 divided by rho squared times u. Now this may remind you of the kinds of gyrations we had to go through for the harmonic oscillator, the differential equation solution method. We're going to examine the asymptotic form of solutions as rho, let's do as rho approaches infinity. So if rho approaches infinity, what we're going to get approximately is second derivative of u with respect to rho is simply equal to u. Okay, so again, this is asymptotically. That means u of rho would be equal to a e to the minus rho plus b e to the plus rho. Immediately we see this is going to blow up as rho goes to infinity. So we have to say that u of rho must go as a e to the minus rho for large rho. All right, that's one way to look at it. Let's suppose rho approaches 0. So we'll look at it, instead of going to infinity, let's let it approach 0. If that's the case, the centrifugal term in the radial equation dominates. We get second derivative of u with respect to rho is equal to l plus 1 divided by rho squared times u. The general solution to that is u of rho is equal to c p to the l plus 1 plus d of d. Rho to the l plus 1, d rho to the minus l. But if rho approaches 0, this term is going to blow up, therefore d must be equal to 0. And we should be able to write u of rho then as c rho to the l plus 1. So we've got an asymptotic expression going to rho goes to infinity, and we've got one where rho goes to 0. And what we have to do is find a way to mesh the two. We know what it looks like for big rho. We know what it looks like for rho approaching 0. We're going to have to figure out a way to make it work for all those values in between. So we got to peel off the asymptotic behavior, and we're going to define a function v of rho such that I can write it as rho to the L plus 1, e to the minus rho, times some other function v of rho. I'm sorry, not v of u of rho. So I've got this L plus, this comes from approaching 0, this comes from approaching infinity, and this guy's going to help us get from one to the other, essentially. We're hoping that v of rho is going to be simpler than u of rho. Let's see. So what do? We operate on it. du d rho is going to be equal to rho to the L, e to the minus rho, L plus 1 minus rho times v plus rho dv d rho. I got to take a second derivative for the Schrodinger equation, and that gives me rho to the L e to the minus rho times bigness minus 2L minus 2 plus rho plus L times L plus 1 divided by rho times v plus 2 times L plus 1 minus rho dv d rho plus rho, second derivative of v with respect to rho. Holy cow. So we're going to take this mess and substitute it into the radial equation and see what we get. Rho, second derivative of v with respect to rho, plus 2 times L plus 1 minus rho dv d rho, plus rho naught minus 2 times L plus 1 times v equals 0. Well, the next obvious step, where else can you look at an equation like this and you're ready to punt. So the only thing you might be able to think of next is to assume we can write v of rho as some power series. When in doubt, let's try that. So I'm going to write this as some power series from j equals 0 to infinity, a sub j rho to the jth power. And of course we have to determine the coefficients a naught, a1, a2, all the way up by some recursion formula. Okay, so what we have to do then is to differentiate v of rho term by term by term. So dv of d rho is equal to sum j equals 0 to infinity, j a sub j rho to the j minus 1, and that's, I can write that as j equals 0 to infinity, j plus 1 times a sub j plus 1 rho to the j. J is a dummy index, so we let it go to j, from j to j plus 1, no harm done. We can still start the series at 0, because even if we started at n equals minus 1, that term would vanish anyway. So my second derivative, dv d rho, we'll write as j equals 0 to infinity, j times j plus 1, a sub j plus 1 rho to the j minus 1. So that's my second derivative term. If I insert all that mess into the differential equation, so I put in dv d rho here, I put in the second derivative here, I'm going to get a complete and total mess. However, what we're going to do at that point is to equate the coefficients of like powers. And if I do that, I'm going to get j times j plus 1, a sub j plus 1, plus 2 L plus 1 J plus 1 A sub j plus 1 minus 2j A sub j plus rho naught minus 2 times L plus 1 A sub j equals 0. This yields a recursion formula, so I can get all subsequent terms of the series. A sub j plus 1 is equal to 2 times L plus j plus 1 minus rho naught divided by j plus 1 times j plus 2L plus 2, all times A sub j. So if I get A sub j, I get all the subsequent terms in the series. And that will give me all the coefficients so I can determine what my power series V of rho looks like. When I do all that, I'm going to find approximately A sub j plus 1 looks like 2j over j plus 1 times j. You can approximate a little bit, which I could also write as 2 times A sub j divided by j plus 1. And we might ask, what power series does this? What power series do we know that might look something like this? Well, the series e to the 2 rho A sub j looks like sum j equals 0 to infinity d sub j rho sub j, and d sub j is 2a sub j plus 1 over j factorial, and this is to the jth power. So a sub j is approximately 2 to the j over j factorial times some factor a. If this were true, V of rho then would be equal to a times sum n equals 0 to infinity 2 to the j over j factorial rho to the j, which I could write as just a e to the 2 rho, which is to say u of rho looks like a rho to the L plus 1 times e to the 2 rho, which diverges as rho becomes large. Okay, so if the solutions diverge, they're not normalizable. And so that's not going to help us. But we can dictate that the series terminates and that there exists an integer, we'll call it a sub j max, that makes the series 0. That means that 2 times j max plus L plus 1 minus rho naught also must equal 0. We define n as j max plus L plus 1. This is what we call our principal quantum number. So rho naught is equal to 2n. And since E, so rho naught is equal to 2n, E is equal to minus m e to the 4th divided by 8 pi squared epsilon naught squared h bar squared rho naught squared. N determines the energy eigenvalues. So E sub n then looks like minus m over 2 h bar squared E squared over 4 pi epsilon naught quantity squared times 1 over n squared, or I can write that as E1 over n squared. That's the result that Bohr had obtained in 1913, but by a completely different method, and of course, the logic here is rock solid. I can solve for a radius, a Bohr radius, which will turn out to be, we'll call it A naught, is equal to 4 pi epsilon naught h bar squared over m e squared. That's the Bohr radius, and it's 0.529 times 10 to the minus 10 meters. So, put it all together. The wave function for hydrogen, then, has got 3 quantum numbers.
1 minute, Dr. Blows.
Well, let's write it out quickly. I'm going to write it as psi NLM is equal of r theta and phi is equal to r sub NL of r, y sub LM of theta and phi, where r of r is equal to 1 over r, rho to the L plus 1, e to the minus rho, v of rho. And v of rho is a polynomial of degree j max equal to n minus L minus 1 in rho, whose coefficients can be determined by the recursion formula a sub j plus 1 equals 2 times L plus j plus 1 minus n divided by j plus 1, j plus 2L plus 2. We'll pick this up next time.